Cool. All right, welcome back. Hope you guys had a good 3-day weekend. It's been a while since I saw you guys. I'm gonna probably be doing most of the lectures until the midterm now. So Professor Janir is busy writing the midterm for you guys. So I gotta let him do that. Yeah, so you'll be stuck with me for a while. And so yeah, today we're talking about sampling. So a few announcements before we start, or yes, weekly goals, I guess. Yeah, so last week we talked about simulation and chances. So we went into the concept of probability a little bit. Talked about how can we calculate the probability of certain events. We talked about a few different ways that we do that. So, went over like the multiplication rule, adding the addition rule. If you have like two kind of mutually exclusive events, you can add them together. And then also just kind of equally likely outcomes and the complement rule. So we'll be kind of reusing those again and again. And then that sets us up really nicely to start talking about sampling. So when you're sampling data from a population, it's important to understand some basics of probability. And so that's kind of why we start with probability first. And then today we go into sampling. And then we'll also see something interesting about the distribution of large samples. So when you sample a lot of data, then something interesting happens with the distribution. And so if you don't remember distribution, we talked about that a couple of weeks back. We talked about categorical distribution, numerical distribution, and how you can use a bar chart to visualize a categorical distribution and a histogram to visualize a numerical distribution. So we're just going to go into a little bit more details about how those distributions can be used with actual data and what those distributions look like as you sample more data versus if you have like a smaller sample. There's some really interesting results that are very important. And then once you go to Friday, we'll go into actually modeling data. And if that doesn't make sense right now, don't worry about that. We'll explain what a model is. But that's going to be kind of the goal going Friday. And then all of next week is just going to be all kinds of different models that we'll use to basically just mathematically represent data in the real world. Yeah, and then a few announcements. So we have a few regrades due tonight, lab 4, homework 3. So again, please take a look at those, make sure everything looks good there. And then we have homework 5 due tomorrow and project 1 due this Friday, but turn in tomorrow for bonus point. And then lastly, we do have the midterm coming up now. So it's going to be on Friday, March 11th, 7 to 9 p.m. Pacific. We'll send out more details and logistics about that. And the scope of the midterms are going to be basically everything up to and including lecture that day. And so that should basically get us through A/B testing and causality. So if you look through the schedule and look through the textbook, that's kind of where we're going to be ending, sort of around that point. Any questions about any of that? Yeah. Oh, what's the format going to be for the midterm? It's going to be just very similar to the past exams. So I believe we have the past exams on the website. If you go to the Data 8 website, we should have materials and like past, let me actually just do this live to make sure I'm not just making up stuff. But I'm pretty sure we have past stuff here. So if you go to resources at the top and then materials, and then here we have past midterms and then the solutions for the midterms. So, I would say, since this is an in-person exam, it's probably going to be more similar to, I would say, probably like spring 2020 and before in terms of like formatting wise. The ones after, or sorry, the 2020, sorry, I'm forgetting the pandemic's like reduces time or whatever. Yeah, so I think basically like after 2020, I guess it's more of like an online exam. So it's still good to study with that, but the format's not going to be quite the same because in online exams, you got to type out the code. Whereas for this in-person exam, you'll be writing code with your hand. So it's slightly different. The questions are like organized in a slightly different way. But it's all the same concepts anyway. So, but yeah, that's a good thing to kind of keep in mind when you're kind of studying. But I think that's the best way to study is go through these past exams, try to go through them. And then if you get stuck on any concepts, get any questions wrong, go back to the lecture and then try to review those concepts that you messed up in the practice exam. But we have lots of practice materials here. And we have practice finals as well, but I would probably say that's less relevant because the final covers a lot of stuff after the midterm, obviously. So I would try to focus mostly on midterms for your study. But yeah, lots of resources there. Cool. Any other questions? Yeah. Yeah, well, you get access to the reference sheet. So yeah, we will have a Python reference sheet. So yeah, you don't have to memorize all the stuff. So we'll definitely have lots of references on like common table methods. Like what does the signature of the function look like? Like how do you call it? So there'll definitely be a pretty big reference sheet there. The goal isn't for you to have to memorize all those things. It's just understand, okay, if I see this method, I know how to use it. I know when it needs to be used. That's the most important thing. Cool, good question. All right, cool. All right, so quick probability review here. So just want to make sure we're kind of wrap up some of the questions that we had last time. So firstly, I wanted to do a quick discussion question. So I don't know if Professor Dinero has done discussion question yet so far, but this is something we kind of classically do in Data 8 in person. That's kind of one of the benefits of being in person. And so basically the way this is going to work is I'm going to show a question on the board, talk to the person next to you, discuss with them for a couple minutes, and then we'll kind of reconvene and go over the answer. And then the folks on Zoom, feel free to like message someone else on the Zoom chat or find a buddy. And then if you don't have someone sitting next to you, that's fine. You can kind of just do it on your own. But I encourage you to try to talk to somebody and talk through the question. It'll just help you kind of think through the problem a little bit better. All right, so here's a discussion question. So we have a population of 100 people, including Rick and Morty. And we sampled 2 people at random without replacement from this population. And so there's 2 probabilities that we're going to try to calculate here. So the first one is, if we sample 100 people without replacement, what's the probability that neither Rick nor Morty is in the sample? So that's the first question. Second question, do that same sampling again without replacement. You can take 2 people out of the population. What's the probability that both Rick and Morty are in your sample of 2? So discuss with the person next to you for a couple minutes and we will go over the answers. All right. Oh, whoops. All right. All right, let's try to go to the answers. Don't worry if you weren't able to get it in that time. Just want to make sure we move along. But we'll go over this together. So for this first question, probably neither Rick nor Morty is in sample. So, you should try to approach this using kind of the methods we talked about last time, right? So usually the easiest way to do it is like, think about if we can separate this into like unique ways that things can happen. And so if you look at this one, like neither Rick nor Morty is in the sample, that means like out of the 100 people, basically I need like the 2 people to only be from the other 98. And so because it can be from the other 98, that's like a lot of different combinations of things I could have happen in my sample. So there isn't just like a few easy ways that this could happen. There's actually like lots of ways that this could happen. And so that's a hint usually that maybe you want to try a different method, such as the multiplication rule. And the multiplication rule works well here too, because it's kind of like a 2-step process. We're going to like sample one person without replacement, then we're going to sample another person. So when you have that kind of multi-step thing, you can use the multiplication rule and it works really well. And so in this case, what you can do is you can basically say, okay, well, what's the probability that in my first draw, I don't get, both Rick and Morty are not in my first draw. Now that I have that, let's see what happens in the second draw and then figure out that probability. So if I'm trying to find what's the probability just from the first draw that I don't have Rick and Morty in the sample, or in that first draw, what would that probability be? Any guesses? Yeah. What's it? 1/98. So, well, we're drawing one person from the sample, and we want to make sure Rick and Morty are not in that like first draw of people, that first person. So you have to look at like the chance that we're not getting Rick and Morty. There's only two like people basically named Rick and Morty in our sample, and we want to make sure it's like the 98, the other 98 people, right? So it's actually going to be 98 out of 100 because you have like 100 possible people that you could choose from, and then I want to make sure like I'm only choosing one of the 98 that are not Rick and Morty. So the first one's going to be basically 98 out of 100. Once you've done that, then we basically look at, oh, sorry, didn't want to do it. Then we look at what's left. And so what's left is 99 people now, once I've taken out one person. And then again, I don't want to get those two people. So it needs to be one of the other 97 that I need to draw. And so then the second one becomes 97 out of 99. So that's how we kind of do it in steps. So just to recap that again, in the first draw, I want to make sure it's one of the 98 people, not those two, out of the 100. And in the second draw, I want to make sure it's the 97 out of the remaining 99. And so then we can multiply them together using the multiplication rule. And then for the second problem, the probability that both Rick and Morty are in the sample, this one's kind of interesting because there's really only two ways this can happen. Like either I'm going to get Rick first and then Morty, or I'm going to get Morty first and then Rick. So that's kind of nice. I can separate it into two events. And then what I need to do is just figure out what is the probability of each of those events. And so the probability that we get Rick first, that's just 1 in 100 because it's just one Rick. And then the probability we get one Morty on the second one, 1 out of 99. And then that's the same probability actually the other direction as well. And so by splitting it up into these two different unique events, we can kind of simplify the problem a bit, and then we just need to figure out what's the probability of each of those kind of unique events. And it turns out the probability is actually the same. And so you just end up multiplying this thing by 2 effectively. But that's how we get the answer there. So any questions about that? Cool. Yeah, so I think in general, like try to see if you can break down the problem into, you know, these smaller events that are kind of can't happen at the same time. And then once you do that, you can add them together. And if you're not able to do that, then that's probably a good hint that either you need to use something like the multiplication rule, or if it gets really complicated, the complement rule can end up being kind of your last resort. So if you're finding that it's like really, really tough and like really complicated, it turns out that maybe find the complement of the event, like the opposite of the event, find that probability might be easier. And then once you find that, just subtract that from 1. So there's a few little tricks there, but that's kind of how we can try to do it. Cool. And then one other question that we didn't get to quite finish last time was the Monty Hall problem. And we won't go into too many details because I do want to kind of move on with the rest of the lecture. But I did want to just like resurface this problem again and go through the solution really quickly too. So Professor Denier introduced this on Friday. Basically, the idea is it's this game show. You have these 3 doors and you choose a door and you're trying to basically get a car. So there's like 2 goats in a car effectively. And so like, unless you're like a really big fan of goats, you probably want to get the car. And so you're going to try to choose a door randomly. Obviously, you have no idea what's behind anything. Once you choose a door, what the host of the show he's going to do is he's going to reveal a door that has a goat behind it. He's going to just let you know, like, by the way, this other door has a goat behind it. Once he does that, then he asks you if you want to switch your decision to the other door that has not been opened yet. And so the question is like, is it better to switch or not? And so it seems at first like it probably doesn't make a difference whether you switch. But it turns out probabilistically that it is actually better to switch to the other door, which is like really bizarre. And we'll go over that really quickly, like why that is the case. So just to kind of illustrate what's happening here, basically what's going to happen is, let's say you picked door 1, and then what he's going to do is he's going to say, okay, actually there's a goat behind door 3, just to let you know. And so now, would you like to switch from 1 to 2? Is that extra information like actually helpful to you or not? So one way to think about this problem before the goat is shown to you is that, let's say I chose door 1 initially, then my probability of getting the car is 1 out of 3. And if I switch to the other 2, those 2 doors, the probability is like 2 out of 3. And so what happens is when he reveals where the goat is in that other set of doors, it's some information, but at the same time, it's not, because you know there has to be at least 1 goat in those 2 doors. There's 2 goats total. So there has to be a goat in those 2 doors anyway. And all he's done is really shown you which door it was behind. But fundamentally, the probability hasn't changed of where the car is. And so it's still 2 out of 3 chance to go to the other 2 doors, even though he's shown you where it is. And so that's how it ends up being more likely. And another way to look at this is to actually just list out all the different possible scenarios, which is actually what we do in the Python demo from Friday's lecture. We didn't have time to go over that, and I'm not going to have time to go over today, unfortunately, but definitely check out that demo. It actually goes through a simulation of looking at how often is switching better than not. And you'll actually see that it's like twice as often that you're going to actually win if you switch. And we can just do this visually actually pretty simply here too. So what we can do is we can just write out all the possible things that could happen. So let's say that for your choice, there's 3 possible things that you could have happened. And for the purposes of making this problem a little bit easier, I'm just going to say there's a car and there's a goat called goat 1, and there's another goat called goat 2. So just to simplify it. And so there's 3 possible choices you could have. So your choice, could have been either goat 1, goat 2, or the car. All right, we don't know what it is, but those are the 3 possible options, right? Each of these is like a 1/3 chance. And then what would the host do? So he would reveal the door that has the goat behind it. So if you chose the first goat, let's say that's where your choice is at right now, he's going to have to show you the door for goats. Oh, wait, that's wrong. Sorry, that should be goat 2 and goat 1. I got these mixed up. Okay, oh, never mind. Okay, sorry. Yeah, sorry. Okay, I got that totally wrong. Yeah, so if Monty's reveal should be goat 2, and then if you have goat 2, Monty's reveal should be goat 1. And then if you're picked the car as your initial door, then he's just going to randomly choose, because if you pick the car as your initial choice, like he could just randomly pick either one, doesn't really matter, but he's going to show you one of those other 2 goats. So, it doesn't really matter. But basically in the first case, if you chose the first goat, he has to show you the second goat. That's his only option, because you've already chosen the first goat, which means if you switch, the choice is the car. And then if you chose the second goat, he has to show you the first goat. And then again, the other choice is the car. And it's only if you've actually picked the goat correct the first, or the car correct the first time, that like switching is like definitely going to be bad for you. And so ultimately, if you just simplify it down, what happens is out of your 3 initial choices, it turns out that 2 times out of the 3, you should actually switch, because that's where the car is actually going to be. And so this is like a nicer, like a little bit simpler way to do it. I'll fix the slides for that second column. Sorry about that. But hopefully that makes sense, that like switching is going to be better most of the time. And sometimes it's not. So any questions about that? Cool. Okay. All right, so that's the Monty Hall problem. Definitely, please, when you have a chance, go look at the simulation from Friday's lecture. It's really cool to see it actually in action and simulate this entire process. It should be at the end of the demo from last Friday's lecture. And you'll get to see like the actual distribution of like how often is it correct to switch versus not. So it's really just nice to see that in the actual simulation and confirm that it's correct. Cool. All right, so all this stuff with probability, all the point of this is to really get us to understand sampling. That's really what we're trying to do here. Like probability on its own is like, it's nice, but in the context of data science, you need to know probability just for the purposes of sampling typically. And the idea is to be able to understand like, where's your data coming from? How rare is like certain kinds of the data, certain kinds of data points. And so sampling helps us with that. And we did a little bit of sampling last week, but we'll do that even more today. And today we're also going to introduce the concept of a random sample. What does it mean to have a random sample? So firstly, let's talk about what a deterministic sample is. Or maybe if we even go back one step before that, what is a sample? So a sample is really just a subset of your population. So if you're trying to study, let's say like all UC Berkeley students, then you could take a sample of like 100 students. So it's just a subset basically of like the entire population that you're trying to understand. And so there's multiple kinds of samples you could take. A deterministic sample is basically a situation where you take a subset, but it doesn't involve chance. So for example, if I was looking at like the registrar of all Berkeley students, and I just take like the first 100 students based on like alphabetically or something like that, that's a deterministic sample. Like every single time I follow that rule, I'm going to get the same 100 students. It's not going to change. And so that's also a good gauge. Like if I repeat this process again, am I getting the same results every single time? That means it's deterministic. So that's a deterministic sample. And then a random sample is slightly different. It should be changing pretty much every time. And there's also some additional requirements. It's not just that it's like changing every time, but before the sample is drawn, you have to know the selection probability of every group in the population. So if I were to sample like randomly from the registrar of UC Berkeley students, I need to know like beforehand, what's the probability that I'm going to get like a geography major? What's the probability that I'm going to get a data science major? What's the probability that I'm going to get a history major? I need to know those things beforehand. I need to have an understanding of what's the probability of each group coming into my sample. That's really important because you might need to make adjustments for that later on. And the real reason this is important is when you look at actual data science and actual data, not all individuals or groups have an equal chance of being selected. So that's really, really important to understand. So it could be the case that certain groups are more likely to be selected, certain groups are less likely to be selected. And that's why it's fundamentally important to understand what is the probability of a group of being selected versus another group. Right, so like, for example, if you're trying to do a survey, like a phone survey, so you're just going to call like a bunch of people at their homes and then try to have them answer a survey over the phone at like a certain time of the day, let's say at like, I don't know, 11 a.m. in the morning or something like that, right? Like that's not, you're not really doing a sample where like everybody's equally likely to be selected in that community, let's say. You know, if people are out of the house and at work, like they're less likely to be able to answer the phone at that time, right? And so it's important to understand like, what is the population? What are the group of people that you're trying to sample? What's the probability of that group being selected based on the way you chose to do your sampling method? All that needs to be taken into account. And so again, that's basically the requirements of a random sample bit. Any questions about that? Cool. All right. So let's actually do some sampling. So here we have, can you guys see this okay? In the back as well? People in the back, okay? Okay. So here we're going to read in a table which is stored in a CSV file. And it basically has a bunch of flights from the summer of 2015. And so you can assume that this has all of the flights, all the domestic flights that United operated in the summer of 2015. And then I've also added here a column called row, which is just going to have the row number. So it's doing np.arange number of rows in here, basically just saying add in all the rows, the row numbers from 0 up to the end of the table. And so that's what we get here. We have this row column at the beginning. So that's just going to help us when we're doing sampling to understand like exactly which row did we sample. We have the date of the flight number, the destination of the flight, and the delay in minutes. So this is like how delayed was it, you know, arriving to the destination. And so we have roughly 14,000 flights here. And so what we're going to do is try to take some samples from this. So one thing we can try to do, if I wanted to take a deterministic sample, here's an example of a deterministic sample. So let's say, so I used to live in New York and I used to fly a lot into JFK. So let's just look at all the flights where the destination is JFK. So I'm going to do United.where destination JFK. And I run this and look at this. So I have only about 600 rows now. So I took this population of 14,000 flights and I've now sampled 600 rows. So 600 individuals. But this is a deterministic sample. If I run this code again, I'm getting the exact same result. The same set of flights are going to come up every single time. So there's no randomness here. I do know what the probability is of selecting a flight from JFK. It's 100%. I do know what the probability of selecting a flight that's not from JFK. That's 0%. So I guess I know the probabilities, but this isn't very interesting. I'm just going to get the same thing every single time. So this is deterministic. Another case of a deterministic sample would be, let's just take every 1,000th row. So out of 14,000 flights, let's just take every 1,000th row and like call that my sample. So I can do that too. So I could do united.take. I'm going to do np.arange 0 to united.numRows in increments of 1,000. And you can see here with the rows, I'm getting the 0th row, then the 1,000th row, 2,000, and so on. And so if I do this again and again, I'm getting the same results every time I run this. So this is another deterministic sample. So again, I am satisfying the condition of knowing what's probability, but I'm not satisfying the condition that this is actually some sort of chance involved here. If the probability is 1 or 0, it's not that interesting. Another thing I can do is also just take some random numbers. So I'm just going to make an array here. So any random numbers you guys want to give me from 0 to 14,000? 3. Nice. Okay. Another one. Another number. 13. Any higher numbers? 6,000. Okay, I'm gonna put it on here because you said it. All right. All right, so this is another sample that we took, right? And this is deterministic. Every time I run this, I'm just getting the same one. All right, so it's not that interesting. If we wanted to actually take a random sample, what we want to do is actually have some sort of randomness involved and like want things to change every time. So one thing we can do, which is going to seem a little bit weird, is I'm going to pick a starting point as a random number. Sorry, np.random.choice. I'm going to make this a random number from 1 to 1,000. So I'm going to pick a random starting point. And then what I'm going to do is I'm going to take all the flights from that are every 1,000th after that starting point. So as I write this out, I'll make a little bit more sense. So I'm going to call it systematic sample. So it is a random sample, but it's going to be like some more structure to it. And so I'm going to go from the starting point all the way up to num rows in increments of 1,000. And then I'm going to do systematic sample.show. So just take a look at this. So I'll break this down to steps here. So basically the first thing I did was I said, let's pick a random number from 0 to 999. So we ended up picking 702. Then take every 1,000th flight from that point onwards. So from 702, then you go to 1,702, then 2,702, and so on. And so if I run this again, notice this is going to change. So right now I had 702. I do this again. Now it's 573, and then it goes on from there. Do it again, 682, and goes on from there. So this is kind of a weird way to take a sample. Like you probably wouldn't actually do this, but this is actually a random sample. Like it is changing every time. There's randomness involved. I can calculate the probability of getting certain things beforehand if I wanted to. I'd have to kind of go through the math and like calculate all that depending on all the chances, but there is a way to know that. And so this is an example of a random sample as opposed to a deterministic example. Cool. So one thing that you need to be really careful about is you don't want to take a sample of convenience. So this is a kind of sample where there is chance involved, but it does not satisfy our conditions of a random sample. So this is basically a situation where you just like sample whoever walks by. So for example, let's say I wanted to understand, like how many people in how many students at like UC Berkeley are going to vote like Democrat versus Republican in the upcoming like midterm elections. So if I wanted to try to get a sense of that, like I could just go stand at Sproul and just like wait for people to walk by and just like ask them. And so that seems like it's kind of random, right? And there's definitely chance involved there. If I went back to Sproul again tomorrow, I'd probably get like a different set of people. It's going to change every single time I do the experiment. But the thing is, I don't really have a sense of like who's walking by. Like it could be students, it could be like a random person who lives in the city who just happens to be strolling through the campus. It could be a faculty member. Like I don't really have a sense. It's really hard for me to figure out like what is a probability of seeing a person from any particular group. And so because of that, it doesn't qualify as a random sample. And so in general, those kinds of things where you're just kind of like, oh, I'm just gonna like wait outside of this building and like just sample people coming out. It's not quite satisfying the conditions that we need for a random sample. So please do not conflate random with just the fact that it's random or like chance as being like a random sample that's like statistically robust and like can be utilized for some sort of understanding of a population. So a slight nuance there. And this basically kind of summarizes it really nicely, actually. So if you can't figure out ahead of time, what is the population that you're actually sampling from? What is the chance of selection for each group in the population? If you cannot figure out those things, it's not a random sample, at least as far as we're talking about in data science. Cool. All right, so now that we know kind of sort of hopefully hammered in what is a random sample, the really interesting thing that you can do with samples is look at distributions of samples. So we kind of already did this when we first introduced distributions a few weeks ago. We did some really cool visualizations. We showed like a categorical distribution, numerical distribution, and distribution really at the end of the day we talked about is just a list of all the unique values and then how often does that value come up. That's really all a distribution is. And so what's interesting about that is if you have a population, you have all these unique values in your population and like different proportions that come up. But then when you take a sample from that, those proportions change a little bit because of chance, right? Like there's a little bit of chance and randomness going on. Like let's say that, I'm just gonna make up a number, but let's say like in the entire UC Berkeley campus, like 50% of students are Democrat, 50% are Republican. If I went and just like sampled a set of like 100 students, right? Like it's probably not going to be exactly 50-50. It's going to change a little bit because every single time I take that sample, there's some chance involved. By chance, I might get more Democrats. By chance, I might get more Republicans. It's similar, even if you're just looking at a flip of a coin, right? Like heads or tails, 50-50 chance if you have a fair coin. If I flip a coin like 10 times, I'm not necessarily going to get 5 heads and 5 tails. I might get 6 heads. I might get 7 heads. If I'm really lucky, I'll get 10 heads. So, it can change every time. And that concept is basically looking at distribution of your sample versus the distribution of your population. There can be differences there, and that's okay. That's to be expected. And so we'll just go over kind of the distinction between those two things. So when you're talking about the distribution of your population, or even just distribution of like some random quantity, such as the flips of a coin, you're talking about a probability distribution. All right, so we're going to specifically call this a probability distribution. And so this is with respect to some random quantity that has various possible values. And the way we're going to define it, it's going to sound similar, but it's a little bit different. So first of all, it's going to have all the possible values, I should say unique values of this quantity. And then we're going to have the probability of each of those values. So rather than like proportion, we're going to say probability. So like heads, probability 0.5, tails, probability 0.5. If I'm rolling a die, it's like 1, 2, 3, 4, 5, 6, probability 1, 6, 1, 6, 1, 6, all the way down. So that's how we think about probability distribution. Think of it like theoretical when I say probability distribution. So this is like theoretically what should happen. If I flip a coin like a bunch of times, theoretically I should get about 50% heads, 50% tails. And so that's basically what we're saying here in terms of probability distribution. And what's interesting about probability distributions is like if you can do the math, then you can actually work out the exact probability distribution of like any random quantity. So for example, like, does anybody play Catan, like Settlers? Anybody here? Yeah. Okay, it's like the greatest game of all time, right? So if you have these two like die rolls, right, and they have to like you count what the number is that they sum up to, that probability distribution is a little bit more complicated than just a single die roll, right? Because you can have like so many different combinations of things. You can go from like 2 all the way up to 12 if you're taking the sum of 2 die rolls, whereas if you just do 1 die roll, it's from 1 to 6. And so it probably starts to get a little bit more complicated. And now imagine you did like 10 die rolls and like took the sum of those. That's going to get really complicated because then you could have anywhere from, I don't know, what is that, like 10 up to like 60 as your values, and calculating the probability of any one of those values is like really, really complicated, but you could do it. Like if you really wanted to, you could write down by hand and figure out like, what's the probability of getting a sum of 24 if I roll 10 die rolls and like take their sum. Could do it, but it's just like really, really annoying. And it's going to take you all day. So that's where Python comes in. So if you have a random quantity like that, where it's like super annoying and really difficult to calculate the probabilities of all your different values, you can simulate it. And we're going to do that a lot in this class, obviously. But oftentimes we'll find that simulation is just easier. And so as we kind of progress through the class, we're going to have even more quantities that are like really, really complicated. They can take on like thousands of different values. And so if I want to calculate like, what are all my unique values? What's the probability of every single value? There's just no way to really feasibly do that by hand. And so you need to use Python basically to at least like approximate it, to simulate from it. And so that's probability distributions. So any questions about probability distributions before we continue? Cool. Okay, so now we have the concept of empirical distribution. So an empirical distribution is what you actually observe. So when I say empirical, just think what I'm observing. Probability, theoretical, empirical, observational. So if I have an actual coin, but I flip it 10 times, what do I actually observe, right? So the distribution of what I observe, that's the empirical distribution. And so as we just talked about, it's probably not going to be exactly the same as a probability distribution. It might by chance, like if I flip 10 coins, I might get 50-50 heads and tails, which is actually exactly the same as the theoretical distribution. So that's great, but that's not going to really happen all the time. There's some chance involved when you're kind of simulating when you're sampling. And so that distribution might change a little bit. And the definition of this is going to look really similar to what we already talked about when we first introduced distributions a few weeks ago. So really, it's just all the observed unique values and the proportion of times each value appears, let's say in your sample. So that's really the only difference. So again, probability distribution, all unique values, the probability of each one appearing. Empirical distribution, all your unique values and the proportion of times that they happen to appear. And so your empirical distribution actually is going to change every single time you sample. Cool. So let's maybe do a demo to kind of actually take a look at this in an example. So we're going to look at our actual population data that we have here, which is the United flights. Or actually, maybe before we do that, let's just look at a simpler example of a die roll. So let's just take, I'm going to make a table that contains kind of the theoretical probabilities for a die roll. And so we're going to have np.a range 1 through 7, which is going to basically give us 1, 2, 3, 4, 5, 6. So these are all the faces of a die. I basically stored this into a table. And then what we can do is we can actually sample from this table. So last week we talked about np.random.choice, which lets you sample from like an array of values. If you have a table, you can just do die.sample, and I can pass a number like 10, and it's going to basically simulate, rolling a die here. So on my first roll, I get a 5. On my second roll, I get a 4. Then I get a 4 again. Then I get a 6, and so on. So you can see kind of all the rolls of your die here, and you can simulate this. And you can do this again and see how it changes. And so every time it's going to be a little bit different here. And so this is a way for us to simulate kind of what's happening. And so the distribution up here, this is effectively a probability distribution. This is a theoretical distribution of what should happen on a die roll. So you have a 1/6 chance of a 1, 2, 3, 4, 5, 6. They're all the same. If I do it over here, this is an example of an empirical distribution. So if we notice here, 5 came out, let's count it, 1, 2, 3, 4 times. So the proportion of 5s in our actual die roll was 4 out of 10. And the proportion of 6s was 1 out of 10. The proportion of 3s was 0 out of 10. There were no 3s. And there were no 2s either. So that's an empirical distribution. And hopefully that makes sense, the difference there between that and a probability distribution. Cool. And then we can actually also take a look at a visualization of this distribution in a histogram. So let's make some bins here. So np.a range, let's do 0.5 to 6.6 in increments of 1. And then let's do a histogram of the probability distribution. So we can just take a look at what that looks like. And so here we see all unique values, 1, 2, 3, 4, 5, 6. And then we can see kind of the chance of each one. So again, remember the y-axis isn't actually the probability, it's percent per unit, it's density. But if you multiply the height by the width, I'll give you a percentage. Cool. And so these ones, each of these should be about 16.66, I think, 1/6, right? So that's kind of should be the probability, the chance of each die roll here. And then if you want to look at the histogram of a sample, we can do that as well. So actually I can take this exact same code, die.histogram, and then instead of just doing the die table, I can do die.sample 10 and look at the histogram of those values. And so if I zoom out a bit, you can kind of compare these. And so if I do this again, it looks really different. Do this again, looks pretty different still. So you can see it's kind of like jumping around, and every single time I do a sample, my empirical distribution changes. And it looks quite different from the probability distribution. But what's interesting is if I start increasing the sample size, so let's say I did 100 samples, then it's still moving around, but it's not as crazy. Sorry, I don't know what just happened there. So if I do this again and again, notice it's still changing, but it's looking like a little bit more similar to the probability distribution. And then if I do a sample of 1,000, now it's starting to look really similar to the probability distribution, right? So it's still moving around, but not quite as much. So that's kind of interesting, right? Like as we increase the sample size, the empirical distribution seems like it's looking more and more like the probability distribution. So that's kind of cool. And it ends up being a very important result actually in statistics. And it's one of the most important things you'll learn in this class. So we're going to go over this slide right now. This is called like large random samples, and specifically the law of averages or law of large numbers. All right, so this slide, I'm going to say it again, very, very important. There's one thing you remember from this class, it should be this slide. All right, so here's how it goes. So if a chance experiment is repeated many times, independently and under the same conditions, then the proportion of times that an event occurs, such as getting 5 on a die roll, gets closer to the theoretical probability of the event. And so we kind of just observed that happen. We did a sample of 10, and it was like, sometimes we never got a 5, so chance of a 5 was 0 out of 10. The proportion of 5 was 0 out of 10. But then as we started going up to like 100 or 1,000, it started to get closer and closer to 1/6. And in fact, all the values got closer and closer to 1/6. So basically all of the possible events got closer and closer to the theoretical probabilities. All right, and so it's pretty interesting, and we're going to see this phenomenon happen for basically like any random quantity. And that's why it's so useful. So when you're doing statistics, when you're actually trying to study some population, you can be assured that like as you increase the sample size, the distribution you're seeing in your sample should be fairly reflective of the sample that you have in your actual population that you're trying to understand. Now, this is useful, but again, in actual data science, like we can't just keep increasing the sample size typically. There's some limits to our resources, like maybe it takes more time, it takes more money to collect data. So you can't always just keep increasing your sample size, even though it seems like that would be like the best thing to do. So there's like limits there, and you have to work with those constraints. But it's good to know that like if you can increase your sample size, typically you're going to be getting data that's more reflective and less variable. So we'll talk about how to adjust for all those things, but in general, that's kind of what we're going to be seeing. Cool. So any questions about law of averages? Yeah. Yeah, that's a really good question. So he said, is there any way to know beforehand, like what is the sample, effectively, like what's the sample size I need in order to get my empirical distribution to be like close to my probability distribution? And so there are actually ways, and we'll talk about it probably towards the end of the semester, but there actually are ways where we can sort of know beforehand. If we understand sort of like the shape of the distribution of our population, there's some assumptions you can make. And then based on those assumptions, you can actually calculate pretty well what sample size you need to be like close to the probability distribution. And it's a really common thing that we do in statistics. And we're definitely gonna do it in this class. So yeah, that's a really good question. Cool. Yeah. Oh, can you call the sample function on an array? I'm pretty sure you can't, but let's try it. I would guess that you can't, because usually when we have these methods, they're usually on like some table. So I don't think this is going to work, but let's try it. Yeah, so sample only works on the table. You should basically use np.random.choice for arrays. In general, we're going to be sampling from tables, I would say. We introduced the concept with arrays, but like you're probably going to be sampling with tables most of the time. Yeah. Yeah.
For the law of large numbers, how is guarantee that our samples are independent of each other?
Oh yeah. So for law of large numbers, how can you guarantee that your samples are independent of each other? So when you're doing your simulations in Python, you can be pretty sure that they're independent of each other. Yeah, it can be tricky when you're doing an actual like sample of like individuals to make sure like you're getting independent data. There actually is like some dependency most of the time. But there's like certain conditions, I guess, where you can sort of like ignore the dependencies if they're like small enough. So a little bit, some of that's a little bit beyond the scope of the class, but yeah, in general, like if your sample size is really large and you have like a systematic way of doing things, you can usually like assume independence or like close to independence. Is probably like the simplest answer, yeah. But really good question. Cool. All right. Cool. So yeah, basically kind of applying this specifically to empirical distribution of a sample. The idea, it's going to sound really similar, but basically if the sample size is large, then the empirical distribution of a uniform random sample resembles the distribution of the population with high probability. And so we say high probability here at the end because we don't know for sure that our empirical distribution is going to match the probability distribution, right? Because every time I run it, it's a little bit different. But there's a good chance that it's going to look similar to the theoretical probability distribution. That's the main thing that it's saying here. And so a cool way to look at this is actually our United data set again. So let's actually just take a look at this one more time. So we have this table again with all the different flights. And so I'm going to make some bins here to visualize the distribution of delays of the flights. I'm just kind of curious on like what these delays look like. I've definitely experienced a lot of delays with United. So I just want to see like what this look like. And so I made some bins here. And so this is what the distribution looks like. So most of the time it looks like the delays are near zero, which I don't know if I really believe it, but anyways, that's what the data says. And then as we go out here, there's like delays going out to the right. And then sometimes it looks like there's negative delays. So the flight arrives early. So if you're really lucky, that could happen to you. I've never experienced that, but you know, awesome if you did. And then, yeah, there's some delays that can be really bad. So you could have like 150 minutes, which is like, that's pretty delayed, you know. Anyways, so you can kind of get a sense of sort of the general shape of the data here and what does the delay look like. And so this is basically a probability distribution. Because if we're assuming that this is, our population is like all the flights in the summer of 2015 operated by United, and I have that data here, that is my population. There's no sampling being done here. This is the population. But if I wanted to sample from this, I could. So let's say for some reason I'm not able to get all the flight records. I can only sample like a few of them. Then we can actually take a look at that and look at what the distribution looks like. So I could do United.sample 10 and then do the same histogram on that and look at the distribution. And so if you look here, you know, it looks kind of similar, but not really. If you like squint your eyes, you can maybe like make the shape out. You know, it's moving around a lot here. But once again, if I make this like 100, so let's sample like 100 flights, now it starts to look a little bit more like the probability distribution above, right? And so that's really all we're saying here is this empirical distribution should look more and more like our probability distribution as we increase sample size. And so we've just applied this now to an actual like population of data rather than like a random quantity such as a die roll, but it's the same kind of concept holds there too. Cool. All right, so we have a few minutes left. I'll maybe just go over the concept. We won't be able to actually do the demo for this, but if I'm looking at all these delays, and let's say I wanted to summarize what I'm seeing in this graph with one number. Any ideas on how I could do that? How could I summarize this for somebody using a single number? Any thoughts? Like I have my distribution delays. I know like sometimes delays are like really bad. Most of the time they're near zero. But if I want to summarize all that with a single number, yeah, median. So median's one way, right? So I could look at median basically says like, let's order all of the different delays and then let's go down. So we're like halfway down our list, 50% of the way. That's the median. So that's one way to do it. Any other ideas? Any other numbers we could use? Yeah. The mode, yeah. So the mode is basically going to tell you like what's the most common number. So in this case, it's like this really tall spike here. That would be considered like the mode potentially. So that's another way you could do it, right? Another way is just to take the average, right? So like sum up all the values, divide by the number of things that we have, number of flights, and that's an average. So there's different ways that we could do this. But all those things you guys suggested, those are all called statistics. So a statistic is basically a way to summarize your data. And that's what we'll try to go more into in the next lecture. But the concept behind a statistic is like, if you can summarize your data by a single number, you can make some conclusions about your population. And there's typically some number in the population that you're interested in studying. And if you can calculate that same number from your sample, that's a good way to make a guess at that number in the population. So we'll go into more details about statistics on the next lecture, but we'll end there. Thank you.